Hello and welcome to this video about circular waveguides. This is part 2 and it follows on from part 1. So far we have gotten this equation r rho from solving the partial differential equation, and it is a Bessel equation. It contains Bessel functions of both first and second degree. And so this is what the formulas are for calculating the Bessel function of first degree. I've also shown the Bessel function in the waveguide. It is like a sine function, only it decreases slowly as we move away from the centre of the waveguide. So this is what the first order Bessel functions look like. They look like sine and cosine functions that are distorted, so that their frequency and amplitude change over time. They both have finite values everywhere. And these are the second order Bessel functions, which look like they have negative infinite values at zero. We'll use this fact to eliminate the second order Bessel functions from the function r. So now to simplify this expression a bit more. The second part of this expression is a Bessel function of second degree. This function is infinite at zero, and therefore would be infinite at the centre of the waveguide, which is at the axis. I've drawn what the second order Bessel function would look like in the waveguide, being infinite at the centre, and so it can't be infinite at the centre. So the coefficient d0 is forced to be 0. So let's work through this calculation more formally. This is what hz is in the waveguide. We've worked this equation out earlier. You can see the Bessel function in hz. And so as we approach the axis or centre of the waveguide, the second order Bessel function approaches negative infinity, and so hz approaches negative infinity, which can't happen. And the points at rho is equal to 0 are along the axis of the waveguide, rho being the distance that a point is away from the axis. And hz can't be infinite along these points, or anywhere in the waveguide. And so this coefficient is forced to be 0. This causes the function r to have this value. And so hz evaluates to be this, which is a very helpful simplification. So now to work on the sinusoidal part of the equation, which circulates around the axis of the waveguide. You can see these sine waves circulating in the waveguide in the picture on the right. This equation describes the repetition of this part of the equation because it repeats every 2 pi radians. So in this case, the number L is an integer. So this implies that k phi is an integer. We'll let this integer be the Greek letter nu, which looks like a V. We'll then substitute this value back into the value of hz to get this equation. I'll just rewrite this equation up here at the top to make more room for more equations. The sum of two sinusoids can be rewritten as this sine function on the left. We can then make this substitution so that there is only one sine term, which greatly simplifies this equation again, since it's better to have no additions in this equation. So we're going to evaluate the fields in this waveguide in the TE mode, that is, the transverse electric mode, so that Ez will be 0 everywhere in the guide. And here's some pictures on the side of how that would look in the guide. The electric field lines only go up and down, while the magnetic field lines called H would have a bit of inclination forwards and backwards in the waveguide. And here's this equation that we get from substituting this into Maxwell's equations. I'm going to derive it in a future video. And since Ez is 0, then this equation simplifies to be this. So the next thing we can do is to simplify the constant term by multiplying these three constants into the one constant term. So I'll just rewrite this equation up the top of the screen so as to give myself some more room to do more calculations. The next thing we have to do is to find the constant Kc, which appears inside the Bessel function. Kc is the cut-off wave number corresponding to the cut-off frequency and the cut-off wavelength. Here is a picture of the waveguide with the electromagnetic wave intensity being a Bessel function of the distance from the center or axis of the waveguide. So this is the next condition of this function, that it is zero at the walls of the waveguide, because the walls are made of a conducting material like a metal, like copper, aluminium or steel, and E phi is zero, because it is zero inside a conductor. So this is what E phi is in terms of the electromagnetic wave in the transverse direction, that is, in the direction along the waveguide or parallel to the axis of the waveguide. And since this wave is in the TE mode, then Ez is zero and is quickly eliminated. We can then substitute the value for Hz into this differential equation. So then we can manipulate this equation into this form, using the rules of partial derivatives. The functions of phi and z are kept constant, while the function of ρ is differentiated. I'll just write the last equation for E phi up here. Now we'll start to find the derivative of this Bessel function j. And so we have to solve for this equation being zero, so that E phi will be zero. J dash will be zero at the walls of this waveguide. I've drawn some black lines representing J dash in the waveguide, so that J dash is zero at the waveguide boundary. So this is the solution to this equation. We look up values for P in a table, where we're given different values for P as a function of the two integer variables nu and n. So this is what Kc is equal to, being the constant term inside the Bessel equation. We can also write it out like this. P is the nth zero of this Bessel equation. And there's this equation, where beta is the propagation constant of the electromagnetic wave through the waveguide, and its wave number, and Kc is the cut-off wave number, and is the wave number of the wave as it reflects off the boundaries, and doesn't move forwards through the waveguide. And K is the wave number of the wave as it reflects off the boundaries and passes through the waveguide. So I'll just write these equations back at the top of the screen here. We can make this substitution for Kc here. The cutoff frequency is when the electromagnetic wave propagates extremely slowly through the waveguide, tending to a velocity of zero, and this is expressed by setting beta equal to zero. When we substitute this condition into this equation, we'll get this equality, that K is the cutoff wave number corresponding to the cutoff frequency. And this is how the cutoff wave number is related to the cutoff angular frequency in radians, c being the velocity of light. After we make this substitution, we get this equation, which will give us this formula for the cutoff angular frequency. And this is the relation between the cutoff frequency and the cutoff angular frequency of the wave in the waveguide. Making this substitution gives us this equation. So this is the cutoff frequency of a circular waveguide of radius a. Now to see if this equation for Hz is correct, we'll start with the wave equation in its simplest form and show that the equation for Hz is correct. We'll expand out the del operator in cylindrical coordinates like this. Then we'll substitute the equation in for Hz, being variable separable. Then we'll substitute the formula for Hz that we've found. We'll calculate this equation one term at a time. Firstly, we'll apply the second derivative of ρ to this equation, which will give us this equation. Then we'll apply this derivative operator, which will give us this equation. Then we'll apply this operator, which is the derivative of phi, so the sine term will get differentiated. And then we'll get this term. And then after simplification, we'll get this term after tidying it up. Then we'll apply the fourth operator. This operator will act on the exponential term, the part of the wave travelling along the axis of the waveguide. We'll firstly get this, and after tidying it up, we'll get this term. And the final operator is just multiplication by a constant, which will give us this term. So now we'll have to add all of these terms up together, which will look like this. And we can factorise out the sine and exponential functions. And then we'll bring the rho squared term outside the brackets too. I'll just rewrite this term at the top of the page, and it needs 2 lines to fit into this slide. We'll define A7 to be this, so that we can work on it separately. So A is now equal to this expression, and so if AZ is 0, then A will be 0. We'll expand out the J Bessel function so as to include its parameter. We'll factorise it like this. Then we'll tidy it up to look like this. I'll just rewrite this equation at the top of the screen here on 2 lines. We'll use these equations that we've defined earlier. Then we'll make this substitution. This is what the function r is equal to. Then we can substitute r into this equation. But this is the Bessel equation that we calculated r to solve, so this equation is 0. So A7 is 0. We can substitute this value for A7 back into this equation, so that we can calculate A to be 0. Now we can say that this equation is correct, and thus our equation for Hz correctly describes the electromagnetic wave that propagates through the waveguide. I found that this particular video had a lot of confusing and overwhelming math that I felt I could get lost in, and I hope that it helps you to understand the mathematics of circular waveguides. So I hope that you have found this video helpful in trying to gain a mathematical understanding of waveguides. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video with other people, and thanks a lot for watching.